Swayam Prabha. Digital India. Educated India.
Welcome back. So, today we will do torque expression for the three-phase synchronous machine. So, initially what I am going to do is slightly I will look into what is known as the synchronous generator. So, the synchronous generator, see, synchronous machine is both used as a synchronous generator and a synchronous motor. So, we were as I was mentioning, synchronous machine has two main applications. One is synchronous generator and another is the synchronous motor. Of this, the synchronous generator is far more common. So, because synchronous generator is far more common, most of our generators are actually synchronous generators. There is no DC generator in the grid. The induction generators are there because of wind farms and things like that. And now you are having more and more PV based thing, that is entirely different story, but they are also generation, but they are converting. Then you could have tidal wave generation and so on and so forth. But the predominant generators which are thermal, nuclear, hydro, gas, all of them are basically synchronous generators. So, we need to get though most of our development of torque expression is naturally driven by the motor application, because in the motor we need to create the electromechanical conversion, has to create the torque which has to balance, be equal and opposite of what the load requirement is for having a steady state speed of operation, steady state mode of operation. But generator application also we should overview, and these are complementary views. These are, it is not like if I am discussing generator, whatever I was talking about in the motor is not valid, or if I am talking about a motor, then whatever I am going to discuss it is about the generator is not valid. It is not like that. But the thing is, when we say generator, what we are trying to focus on is the induced EMF in the stator winding. So, what we are doing is, rotor has a magnet, either a electromagnet or a permanent magnet, usually electromagnet, and then, so how do you create the electromagnet? You create the electromagnet by sending the DC current. So, your omega r is therefore 0, and you rotate the shaft, you rotate the shaft at synchronous speed. You rotate the shaft at synchronous speed. So, therefore, this frequency condition which we are now encountering again and again, we discussed single phase synchronous machine, we discussed two phase synchronous machine, now we are going to discuss the three phase synchronous machine, which is really the most common application. So, this frequency condition is satisfied. If the synchronous machine is not rotating at synchronous speed, which means that the supply is at, let us say 50 hertz, but the machine is not rotating at 50 hertz, then this frequency condition will not be satisfied. Then you have already seen in the single phase and two phase machine that the average torque will be 0, same thing will come out here also. Hence, the name synchronous machine, it has to be rotating at the synchronous speed to generate average torque and average power. And by going to two phase and three phase balanced synchronous machines, what we are ascertaining is that we, for a balanced system, the torque will be, instantaneous torque will be equal to the average torque, and instantaneous power will be equal to average power, because speed is constant omega s. So, therefore, the other statement automatically follows from this. So, let me know. So, what happens in a synchronous machine? I have said this again, and it's good, it's fine. You are rotating the electromagnet at the synchronous speed. On the stator there are 3 windings, A phase, B phase, C phase. Now comfortably I can say that these windings are distributed in space, and you know why we distribute them in space, because we can, in that case, the spatial distribution of the MMF due to any winding is sinusoidal in nature. This helps in creating proper rotating travelling waves, which are sinusoidal rotational travelling waves. It helps us in creating, essentially at the end of it, what it means is that the main voltage that you generate at the terminals is only sinusoidal, and the harmonics and other contents are eliminated. So, these things we are seeing again and again, and these are subtle concepts. So, I keep on mentioning them so that you keep revising those concepts if required, going back to the previous lectures and things like that. But while illustrating it, unfortunately I have to show them as concentrated windings, because that makes my life easier in sketching and things like that. Now, synchronous machine, the DC rotor, the rotor, which is a magnet or an electromagnet, which creates a sinusoidal distribution of flux or B in the space, rotates at the synchronous speed. So, now you have A phase winding, you have B phase, you have B phase winding, and you have C phase winding. So, whatever EMF is seen in the A phase, same thing will be seen T by 3, where T is the time period, later by the B phase, and then same thing will be seen by the C phase 2 pi by 3 time period later, being a in steady state condition. So long as each of the windings are connected with the are either open circuited or are connected exactly with the same load. So, like if you have put 5 ohms on one phase, you have put 5 ohms on another, 5 ohms on third. Suppose the first phase is at unity power factor, second is also at unity power factor, third is at unity power factor. If the first phase is at 0.8 lag, then the second is also at the 0.8 lag, and the third is also at the 0.8 lag. So, balanced system operation is, all this instantaneous power is constant, instantaneous torque is constant, all this discussion is only pertaining to balanced system. So, when the magnet is rotating and the winding sees rate of change of flux, induced EMF is generated. If there is nothing connected, open circuited, then the PM required for the steady state rotation is 0, because speed is constant. I have neglected friction, windage losses, all that kind of other parasitic losses in the machine. Then what happens? There is no electric output. So, there is no mechanical input also required, and once you set up the speed, it is like a perpetual machine which will keep on running under ideal conditions. Now, I connect load, maybe if, like I said, 5 ohm load at unity power factor or whatever, I connect some load onto it. The moment I connect load, the rate of change of the EMF, rate of change of flux, which has created induced EMF, will circulate the current through the resistance, which is E by R if it is just a pure resistive load, and this current is created in such a way so as to oppose the change. So, therefore, it means by the BIL principle, the F equal to BIL principle, because we will always ascertain that the conductor is vertical, then the flux lines are horizontal and things like that. So, it is 90 degrees. So, sin theta is 90 degrees. So, it is just not really not L cross B or something like that, just sin theta is 90 degrees, and so by it is just simple BIL principle, as I called it. If the shaft is, so this is the coil, then if the if let us say this coil is being rotated in this direction, then it will automatically create a force or a torque in the opposite direction, because it is opposing the change. That is the thing. So, this side we are Tm, this side is the electromechanical torque Te, and for steady state Tm has to be equal to Te. So, then only you will have a steady state operation. So, control systems is required, and many things we will come to those things you will come in electrical power systems class later on. And this Tm minus Te, if it is not, then the you have J, the moment of inertia, into d omega by dt should be equal to Tm by Te. When Tm when Tm is equal to Te, then the omega becomes constant, which is our synchronous speed at which we get necessary things going on. Now, let us think of let us think of, okay, let us say that this is my stator, and this is the stator. Let us say I have created a notch here, and a winding is placed here, and this winding, let me call it as A dash, and I have a magnet with the tapered pole face north south. Actually, its width is more than what I have seen. So, this is the stator axis, and here the stator magnetic axis and the rotor stator magnetic axis and the rotor magnetic axis are aligned. So, they are exactly aligned, but in general, because the rotor has to rotate, so in general it is better to think of this tapered magnet having electromagnet making an angle theta with the theta with the stator magnetic axis. So, the rotor magnetic axis makes an angle of theta with respect to the stator magnetic axis. Okay. Now, my question, $1,000,000 question is, what is the flux linkage lambda A of t, lambda B of t, and lambda C of t? Once I know this, okay, then automatically E A will be N A d lambda A by dt, E B will be, actually I will number of turns symmetric construction. So, the number of turns on the stator are going to be the same. Once I get E A, I can automatically write the expression for E B and E C. I do not have to really do this. Once I write this, I can write the expression for the induced EMF associated with all the 3 phases. Once I know the induced EMF, then if your resistance is connected or any load is connected, I can proceed forward to calculate the current and so on and so forth. That actually can be done much more easily if you have a equivalent circuit, if you write a equivalent circuit of a synchronous machine, which we will develop in the subsequent lectures. Let us for the time being focus on this particular job. So, I want to see what are the flux linking the what is the flux linking my A phase winding. So, let me rub out everything else here. so that I can use the figure and writing both of it simultaneously, easier that way. So, your figure is here. Now, the pole faces are tapered so that the flux which they create, the B, let us call this as B created by rotor, B created by the rotor winding as a function of theta, as a function of alpha. So, now you have two variables here, alpha and theta. So, I am writing flux created by the rather the flux density or B which is created by the rotor is by proper construction of tapering of the air gap, which means that at the center it is least and then it keeps on increasing. If the air gap increases for the same MMF, the B is inversely proportional. So, lot of those things have been properly taken care of, it means it reduces, and I have achieved, let us say for the sake of discussion, that it creates a sinusoidal flux pattern. So, what it means to say is that you have strength of the B lines here is maximum and then it keeps on reducing, and finally becomes 0 when you reach the 90-degree axis to this. So, there is no flux lines which are being created. So, the B lines number of lines per unit width or whatever is highest near the center face, and then they keep on reducing until when you reach at 90, nothing is created around the quadrature axis, and therefore, the B that is being created is given by B of alpha equal to Bm cos of alpha minus theta. So, what does it mean when alpha is my variable here? The primary variable is alpha. When I rotate the machine, theta will also become a variable, but right now I am not rotating the machine. So, therefore, it is just that the rotor is kept at an angle theta, and then we are asking the question, how is the flux, how is the B waveform seen across the air gap? And the answer is at alpha equal to theta, the answer is at alpha equal to theta, this is alpha equal to theta, the B is peaking here. So, therefore, cos of this becomes alpha equal to theta, this becomes 1, and then it keeps reducing, B keeps reducing with a sinusoidal distribution, and therefore, it reduces as per Bm cos of alpha minus theta. When alpha becomes equal to so when alpha becomes equal to theta plus minus pi by 2, then B will become 0. When alpha is 0, then the B will become, B is at its maximum, and so you have a sinusoidally distributed flux in space. And if you rotate the rotor at the angular speed omega s, then what will happen? You will basically get Bm cos of a rotating wave flux wave, which is described by theta minus omega s of t. This is how the B of t will look like if the rotor is rotating at synchronous speed, which is to say that this is, now here the theta is variable and this is the B wave at initially at theta equal to 0. Let us say you had when the magnet was centered around the stator A winding axis. So, you created a cos of omega t kind of a proton. South pole side, it is everything is south pole side everything is negative B, north pole side everything is the positive B, and then this is the when the ns pole is aligned with the stator axis, this is how it is, then it starts rotating. So, this whole sinusoidal thing starts moving with a speed of omega s. So, it will create a travelling wave like this, but I do not need travelling wave right now, but in your mind I am trying to build up the picture. Right now here everything is like rotor is kept at angle theta, I am not rotating anything right now, and then I am asking, please tell me what is the flux distribution across the space. So, because this is already one variable rather this theta has already been taken, I create a primary variable alpha and write Br of alpha is equal to Bm cos of alpha minus theta. Now, see, if you take us, because Bm is varying, you can't just do B times of A. So, what you have to do is you have to do this B times B at an alpha, then you look at the small ds strip there, a small ds strip here, suppose you are at an angle alpha, this is the stator axis, and sorry, so you look at some small angle alpha, and then what happens, the ds is going to be, if this is the, if the shaft here inside has a length L, okay. So, it has a length L and you are looking at a small arc somewhere here, a small arc somewhere here, wherever it could be here, I am sorry, it could be here, it does not matter. You have to integrate from here to here to see what is the, because all the flux lines are going outward here and all the flux lines will be coming inside inside here. So, if I want to find out what is the flux which is linking this coil A dash, then I have to, for all of that which is going outside, I have to do the integration, and because it is varying like this. So, what I need to do is B r alpha into the arc is, this is the arc, small arc centered at a radius r and an angle of d theta will create an arc of this r d theta, and then this has a depth of L. So, the cross section area becomes B r alpha cos of this, and this small strips of fluxes that are being linked with this coil, I have to integrate it from minus pi by 2, I have to integrate it from minus pi by 2 to theta minus pi by 2 to, this should be alpha, I am sorry, alpha is my variable, and I should link it from theta minus pi by 2 to theta plus pi by of 2, and this will give me the flux which is linking the coil A. Yeah, the where is this point, where is this with respect to this is the stator magnetic axis, right. What is this point? Minus pi by 2. Where is this point placed? Plus pi by 2. What is this distribution given by Bm cos of alpha minus theta? Now, I have to integrate from here, start the integration and go up to here. So, where should, or I should start from here and go up to here. So, the lower end of the integration will be minus pi by 2, upper end of the alpha. So, this is alpha equal to minus pi by 2, this is alpha equal to plus pi by of 2. So, therefore, the lambda of A of t, lambda of A of t is going to be equal to, and these all angles are with respect to what? These all angles alpha, theta, everything are with respect to the stator A phase magnetic axis. This is stator A phase magnetic axis. That is why this point is with stator A phase magnetic axis, this point is at plus pi by 2, this point it is as minus pi by 2. So, now stator number of turns are all A, B, C phases have same stator number of turns. So, I will just write it as this B. So, this is NLR, and then I will write this as Bm cos of alpha minus theta d theta from minus pi by 2 to plus pi by 2, and then this will be written as Ns LR Bm sin of alpha minus theta from plus pi by 2 to minus pi by 2. So, therefore, it is Ns LR Bm cos 2 times cos of theta. So, the lambda of A of t becomes equal to 2 Ns LR Bm cos of theta. Now, if the rotor was having an initial angle of gamma and was rotating at a synchronous speed omega s of t, then the flux which will be linking it will become sinusoidally, will have a sinusoidal variation in time, and the induced EMF being d lambda A with respect to dt, it will become 2 Ns LR Bm. When you differentiate cos of omega s of t, it is going to be minus of sin of omega s t plus gamma, and then one more omega s of t. Because of that, one more time the omega s has to come out outside, and because cos of 90 plus theta is minus sin theta. So, I can write it as 2 Ns Bm LR into omega s times sin of cos of omega s t plus gamma plus pi by 2, which can also be written as Em cos of omega s t plus gamma pi by 2. So, if I want to calculate the RMS value of the induced EMF, then it will be Em by root 2, which is 2 pi Fs by root 2 into Bm LR into 2 Bm LR into 2 Bm LR into n of s. But we know that 2 by root 2 is 2 pi, this will be 4.44 Fs, 4.44 Fs, root 2 into pi, that will give you 4.44 Fs, Bm 2 Bm LR into n of s. So, something similar to the transformer equation you are seeing here. So, therefore, this is what I will get. So, these volts which are RMS value which is created, you can see that it is proportional to frequency of the rotation. Higher the B that you create, stronger the magnet you or the electromagnet that you use, larger it will be. Bigger the machine, the bigger the radius, more longer is the length of the machine it will be, and also more the number of turns, the more will be the RMS value. So, all of these are very intuitive thing. This also tells you why aircrafts etc., they work at higher frequency AC supplies like 400 hertz and so on, because the space is at premium. If I want to get the same induced EMF, then I should try to then use larger BMs and I should, because this is being compacted, you should, one simple solution is to increase the speed of the rotation of the rotor to generate the necessary value of the voltage. Now, this being the A phase voltage, this being the, now that we have calculated this A phase voltage, the B phase voltage and the C phase voltage will be lagging the A phase voltage by time. Whatever is happening in the A phase voltage, same thing will happen T by 3 time later, the same effect will be seen in the B phase, and 2 T by 3 times later it will be seen in the C phase. Therefore, you get an angle of minus 2 pi by 3 minus 4 pi by 3, and the 3 phase synchronous machine is a balanced machine. This lambda s that we described, the lambda s that we described, how did we describe the lambda s, the flux linking this, was described as 2 ns bm lr cos of omega t plus gamma or omega s of t plus gamma, and the induced EMF came as something em cos of omega t plus gamma plus pi by 2. So, therefore, phasor perspective, this is the, if this is taken as the flux phasor, anything which is sinusoidally distributed in space, cos of omega s of this, you read it as cos of omega t plus gamma. So, anything which is sinusoidally distributed in space and also at our synchronous frequency can be represented by a phasor, and similarly this can also be represented by a phasor, where of course, the RMS value is Em by root 2 is shown here, and this also should be taken as the RMS value. So, the voltage phasor is leading the flux linkage phasor, corresponding flux linkage phasor by 90 degrees. Now, you know that actually these windings are distributed, I have discussed distributed windings earlier, they are distributed in space. So, because they are distributed in space and they are then connected in series, so the effective voltage is going to be the a bit less than just the superposition by Ns, and that is basically that winding factor which we have discussed earlier. So, actual induced EMF will be given in the A phase, will be given by some such equation. Now, you have seen that because of the sinusoidal distribution of the flux, only sinusoidal, only fundamental component voltage is being generated. No other component is being generated, which is exactly what we want in reality. Okay. Now, let us move to, let us revert back to our standard discussion based upon the motor convention, based upon the motoring action, where we want to calculate, what is the torque which is being generated on the shaft of the motor. So, I am again going back to my convention, which I am again going back to the convention which I was having in the with respect to the single phase rotating motor and the two phase balanced rotating motor, which is that the electrical input is being given to the windings. There is a load connected on the shaft of the motor, and then because of the electromechanical energy conversion, the torque is generated on the rotor shaft, and that starts rotating the rotor, and therefore, mechanical work gets done. So, generator convention, usually we say current is coming out of the winding. So, if this is the winding in A phase winding, the generator convention will show current being coming out of this, where this is the A and this is the A dash, so to say. Then the motor convention is for the same A dash polarity, the current is going in. The generator convention for the A dash is this, the motor convention is of current is this is the generator convention for the current. Okay. Small simple things, but you should keep everything properly compartmentalized in your mind, rather internalize it. It is not like you have to remember anything, but you have to just internalize it. Once you internalize it, whatever you need it, it will come back to you automatically. Okay. Now, what is the when I say I am linking back to the previous lecture and I am going to calculate the torque, electromechanical torque which is generated on the rotor, then what is it that I have to do? Current is being fed in the A phase winding, B phase winding, C phase winding, and I will not work with the rotor now being I will assume that the rotor is the magnet on the rotor is being set up as a electromagnet, a distributed winding which creates a distributed flux here, and it for that requires a current IR, necessary current IR to be set up in the rotor, which is the DC current. So, there are 4 windings A, B, C distributed on the stator carrying IA, IB, IC, and a fourth winding which is the rotor winding DC winding carrying the current. Now, so if with this what first thing that we will do is, so we have to calculate the flux linkage with A phase, flux linkage with C phase, flux linkage with A, B and C phases, flux linkage with the rotor winding. Then once we have got the flux linkages, then we will apply this principle to calculate the co-energy. Once we have calculated the co-energy, then we will take the derivative of this with respect to theta, and we will generate the electromechanical torque which is being created. So, to do all that, we need to calculate to do all that lambda in terms of I. Basically, we need to calculate all the 3 self inductances LA, LB, LC, which are all going to be same. The self inductances are all being same because the 3 windings are exactly identical. So, therefore, their self inductance only they are distributed in space, but otherwise number of turns, their distribution, everything else being everything being same, the 3 self inductances will be identical. And then we have to calculate LR, which is the self inductance of the rotor winding, because it is also now I am talking of a cylindrical rotor. So, the LR will not be a function of theta, it will just be a constant thing. If you excite a cylindrical rotor is there, air gap is constant everywhere, and wherever, and if I put a current IR, then whatever be the theta, the geometry which is seen by the rotor is the same. So, therefore, the LR will also turn out to be constant. So, we will assume that that LR I am not going to calculate, I will just assume that it is some LR. This self inductances I am going to calculate for the A phase, B phase, C phase, the LS I am going to calculate, because then I am interested in what is the mutual inductance between the 2 stator windings MAB, then what is the mutual inductance between B and C, and what is the mutual inductance between C and A. And I am going to show that this is minus of Ls by 2. So, this to show this I need to calculate this, and then I also, so these are the 3 mutual inductances between A, B and C, the stator windings. They will have fixed value because the stator windings are not rotating. So, therefore, they will have fixed values, but when I look at MAR, in addition I will need MAR, MBR and MCR. What are these MAR, MBR, MCR? The mutual inductance between the rotor winding and A phase, rotor winding and B phase, rotor winding and C phase. The C phase is being A, B, C phases being on the stator, and these will be functions of theta. They have to be functions of theta. So, let us start by this. Let us look at this picture. Let us look at this picture. So, this is the A phase, this is the A phase axis, of the stator winding. I am marked it as AA dash. Then 120 degrees later, so this makes 90, then this is somewhere here. So this will be my B, this creates a magnetic axis of A. Then 120 degrees later, when I put the B dash, then it creates its magnetic axis, which is 120 degrees apart, this one shown here. And then the C phase, after that I have 60 degree gone, 60 degree gone, then I start my C winding, and correspondingly the return part C dash, then it will create a magnetic axis which is somewhere here, which is another 120 degree apart. So this is the geometry. Now first self inductance, I need to only worry about this, there is, these are unexcited, so I do not need to worry about. So I will have, because they are distributed in space to create sinusoidal flux distribution. So I will have the flux distribution in space, and because I a is a function of time. So therefore there is a time variable also shown here. This is ns I a cos of alpha. Alpha is the variable used to traverse across around the rotor. Now because this is the stator, there is a because there is a somewhere a rotor, you have, I have not shown here rotor, but you can see, imagine this rotor here. So and the stator, there is also a third coil sitting here. So you will traverse, you can see it here, you will have a this is the rotor, this is the rotor. So the flux, when the flux which is created in this stator winding, the path it will take something like this, we will see a gap of G here and see a gap of G here, and mu r is taken as, mu r is taken of for the iron, is iron taken as ideal, the mu r is going to be 0. So any H into L effort which is spent is only in the air gap, and you have air gap of length 2g. So therefore ns I a by 2g becomes the H, multiplied by mu naught, and that becomes the B, and that is the peak value which distributes in cosine fashion. So therefore BA alpha of t becomes mu 0 ns I a by 2g cos of alpha. And then this being the magnetic axis, all the flux which is being linked, I have to move from minus pi by 2 to plus pi by 2 to find out what is the flux which is linking the A phase winding. So I write this LRD alpha, we know now how, where from this LRD alpha has come, we know where from this has come, and this will give me the flux which is linking the A phase winding. I have to multiply that by ns, the number of turns on the stator, to calculate flux to be converted to flux linkages. So substitute this here. So ns into ns gives me ns square, IA comes here, mu 0 by 2g, mu 0 by 2g comes here. Only the function of alpha is the term which corresponds to cos of alpha, which is to be integrated from minus pi by 2 to plus pi by 2, and this integration will give me sine of alpha, cos of integration of cos of alpha is sine of alpha, which from minus pi by 2 to plus pi by 2 will be 1 plus 1, which is equal to 2. So therefore the lambda A of t will turn out to be 2 times mu 0 by 2g ns square Lr Ia of t, and the ratio of lambda A of t by Ia of t, and the B phase and the C phase are unexcited when we are calculating the self inductance. So therefore this Ls, which is ratio of lambda A by Ia, will turn out to be mu 0 ns square Lr by g Henry. So this becomes the self inductance of the, machine in Henry. Now, let us look at the mutual inductance. What is the relationship? What is the mutual inductance? I am looking at, strictly speaking, I am looking at MBA. And what is the MBA? MBA is the flux linking the B phase due to current in the A phase. This is MBA, and because you know that mutual inductances are symmetric. So, I do not need to calculate MBA and MAB separately, the same thing will be equal to MAB. So, now what is happening? Current is there in the A phase. Where is the flux we are how much flux, what we are trying to find out, how much flux is linking the B phase. So, therefore, NSIA is the MMF, right. This is basically the MMF, which is distributed in space as NSIA cos of alpha divided by 2G. Everything is all that MMF is created in A phase. Even if I want to measure the effect on B phase, the way it is created in A phase currents will create MMF in space, which is exactly the same. The B is exactly the same. A phase, just because I want to measure some effect on the B phase, the B which is being created by the current which is flowing in the A phase is still the same. No, there is only one current which is flowing, and that is in A phase. And the question being asked is, what if the question being asked is what is the B distribution in the air gap, then the B distribution in the air gap is just given by this. So, therefore, this whole thing is exactly the same here, whatever is here, exactly the same thing is calculated here. Then the area of cross section is also, the small elements ds strips are all RL d alpha. So, RL d alpha strips are exactly also are exactly the same way like this. Only thing, then the number of turns which are there on the this is the number of turns on the B phase, they are also exactly same as that on the stator. So, A phase. So, therefore, the number of turns on the B phase are also written as NS only. Now, only thing that is to be changed is the limit of integration. For the flux which is linking, this is the axis of the B phase. So, this is 2 pi by 3 with respect to the A phase stator axis, the vertical one. So, from here 2 pi by 3, I have to go for B dash minus pi by 2 behind, and for here I have to go plus pi by 2 ahead. So, therefore, only thing that goes under change is the limit of integration from 2 pi by 3 minus pi by 2 to 2 pi by 3 plus pi by 2. So, Ns into Ns will create Ns square, because both the A phase winding and the B phase winding are having same number of turns. So, mu 0 Ns square by 2G RL, this Ns should not come, this Ns should not come, R times of L, all that comes out. Cos of alpha, when it is integrated, it became sin of alpha. Only the limit of integration is now not pi by 2 and minus pi by 2, but 2 pi by 3 plus pi by 2 and 2 pi by 3 minus pi by 2, or in other words minus of pi by 2 minus 2 pi by 3 to pi by 2 plus 2 pi by 3. And so, this means it is cos of it is going to be yeah. So, it is going to be sine of pi by 2 plus 2 pi by 3 minus of sine of minus of pi by 2 minus of 2 pi by 3. So, this first term is sine of 90 plus theta is cos of theta. So, cos of 2 pi by 3, and then this minus of sine of minus theta is minus sine theta. So, minus minus will become plus. So, this will become plus, and then sine of pi by 2 plus 2 pi by 3 is going to be cos of sine of pi by 2 plus theta is cos of theta. So, therefore, and another cos 2 pi by 3, and cos of 2 pi by 3 is minus of half. So, therefore, it will become minus of half plus of minus of half means minus of 1, and so this term will come out to be mu 0 n s square R L by 2 g. Now, what was the self inductance? Self inductance was mu 0 n s square R L by g, and here it is mu 0 n s square R L by 2 g with a minus sign. So, therefore, the mutual inductance, so therefore, MAB is going to be equal to minus of Ls by T. Then the same way MAC, the same way MAC will also be minus Ls by T, Ls by 2, MBC will also be minus Ls by 2. So, all the stator side mutual inductances are going to be minus of Ls by 2, where Ls is the self inductance of the all the 3 A phase, B phase, C phase stator windings. Now, let us try to write the equation for, let me try to do this here, let us try to write the equation for lambda A, lambda B, lambda C and mu r. Why am I writing it? Because later on I have to calculate the co-energy associated with this system, and my state variables are I A, I B, I C. So, let us write one equation first, then we can immediately infer the second equation. So, the current linking the stator A phase winding is its own self inductance times its own current plus the mutual inductance between A and B, which is minus L A by 2 times the B phase current, and then the mutual inductance between A and C, which is minus L S by 2, these are all constant numbers, times I C, and then the mutual inductance, the flux coming due to the mutual inductance between the rotor, which is at a position theta, having let us say the mutual, when theta is equal to 0, when it is the rotor winding is exactly aligned to the rotor winding axis is exactly aligned to the stator winding axis, then let us say at that time the mutual inductance is MAR, and you can try to attempt this calculating this MAR. This MAR will depend upon two things, both the number of turns on the stator and the number of turns on the rotor, and they are not necessarily same. So, the stator could be having 100 turns, rotor could be having 50 turns. So, therefore, I cannot use the same Ls and minus Ls by 2 or something like that, I cannot do. I have to use another constant here called MAR, which is the maximum mutual coupling which can happen between A phase and the rotor, which will happen when the rotor axis exactly aligns with the stator axis. But then when the rotor moves an angle theta degree, then from our previous work we know that this mutual inductance will can be considered to be sinusoidally distributed. It will reduce, mutual inductance will reduce from MAR to MAR cos theta, where theta is the angle between the rotor axis and the A phase stator axis. So, you will get the flux linking will be given by MAR cos theta into I of R. This is the third component. Sorry. Yeah, sorry. So, now when you are talking of the B phase, when you are talking of the next phase, the B phase current, then its linkage with respect to A phase is having a mutual inductance of minus Ls by 2. So, the flux which will be created will be minus Ls by 2 into Ia, then its own self inductance being Ls, it will, the flux linkage which will be created will be Ls into Ib, then between B and C again minus Ls by 2, So, therefore, mutual coupling Ls minus Ls by 2. So, the term flux linkage term is product of minus Ls by 2 into IC, and then whatever happens in A phase, the flux linkage see the rotor is creating flux linkage with respect to A phase winding, that is given by MAR cos of theta. Then same thing will be seen by B phase when the rotor is rotating, but because the B phase will be encountered 2 pi by 3 angle later. So, therefore, this will have to be shifted, phase shifted by minus of 2 MAR cos of theta minus 2 pi by r, and then the C phase will be minus Ls by 2 minus Ls by 2 Ls MAR cos of theta minus 4 pi by 3 or cos of theta plus 2 pi by 3, and then when I am writing here, this is going to be MAR cos of theta times of IA. Now, flux linking the rotor winding due to A phase current is MAR cos theta into IA, then MAR cos theta minus 2 pi by 3 times IB plus MAR cos theta by 2 plus 2 pi by 3 times of IC plus of LR plus of LR times of IR. So, this will give me the this, I have it written here more neatly written here. So, I get a 4 cross 4 matrix. The inductance matrix here is a 4 cross 4 matrix. Now, we calculate the co-energy. So, how do you calculate the co-energy? I will be a bit short this time in my description. So, I rotate, I first of all create the correct assembly, which is bring the rotor at an angle theta with respect to the rotor axis at an angle theta with respect to the magnetic axis of the A phase. Then I excite just the A phase current. When I excite just the A phase current, then I am going to do this lambda A DI kind of thing. Since IB, IC, IR are 0, so only the self inductance term is going to be created, which is half of Ls IA square. Then I increase the B phase current from 0 to IB, while the IA is now held at its appropriate value and IC and IR are still 0. So, I will get a term which is corresponding to its own self inductance, which is half of Ls square, and a mutual this M here is minus Ls by 2. I am just not writing every time minus Ls by 2. So, this M here is minus of Ls by 2 minus of Ls by 2 into IA times of IB. So, this term also we have seen in the previous lecture how it comes, and then so I have accounted for this, I have accounted for this, I have accounted for this. Then I will excite the C phase current. When I excite the C phase current, keeping A and B phase current stator at their values, I will get a term which corresponds to half of Ls IC square, then minus of M IA IC minus of M IB IC. I will get these three terms. Now, this so far, because stator assembly is all constant and I am taking a cylindrical rotor and all that kind of stuff, this none of these terms is a function of theta. So, they will not actually be responsible for creating torque, but we have to write them properly to derive the co-energy equation. The real interesting terms come when I excite finally the rotor current from 0 to IR. So, the integration variable will be dummy variable dir dash, and then we keeping so the what is happening is that you are having this lambda r IA, IB, IC, and these are all set to their proper values, then IR dash this theta. So, everything is now properly excited, dir dash. I am looking at the contribution which is coming out of this to IR, and for that I have to first write all that equation minus of MIA minus of MIB minus of MIC plus LR IR dash plus, I am sorry, this is MAR cos of theta. I just explain one term, final one, just so that if you have forgotten what the way we used to do it earlier, then it will come back to you. Theta minus 2 pi by 3, this term will be minus of MAR, sorry, plus of MAR cos of theta plus 2 pi by 3 into IA, IB, IC, and then LR dash IR dash, and then we are doing lambda I DIR dash from 0 to IR. So, therefore, I have to pick up this, copy, paste it here, and integrate this from 0 to IR with respect to DIR dash. So, therefore, because with respect to the IR dash variable, with respect to the IR dash variable, MAR IAR cos theta is a constant. So, the contribution that will come from the first term will be MAR cos theta IAIR. Similarly, for the second term and third term. So, let us get back to it. Now, you know what I am actually doing. So, the contribution that I will get, contributions that I will get, M cos MAR, M A phase to rotor, peak A phase to rotor. So, MAR, or I can even just use the term MAR. Then the other, all others are here also, the peak will be MAR. So, IA IR MAR cos theta, then IB IR MAR cos of theta minus 2 pi by 3, that is the peak. MAR represents the peak magnetic mutual inductance that can happen between any stator winding and the rotor winding. And then ICIR MAR cos of theta minus 2 pi by 3, and its own term related to related to the self inductance, which is half of LR IR square. This also you can see it here. This also you can see somewhere here. When you integrate this with DIR dash from 0 to IR, then this LR dash DIR dash integration will give you IR dash square by 2, and that term will therefore bring me, that term here will bring me this term half of LR IR square. Now, when I take the, to calculate the torque, I have to take a partial derivative with respect to theta. So, 1, 2, 3, 4, 5, 6, 7, the first 7 terms do not have anything in terms of theta coming from them. So, therefore, they will not contribute, their partial derivative with respect to theta is 0. So, the only things which involve explicitly theta are the 8th, 9th and 10th term. So, the last 3 terms require that. So, I have Wm dash with respect to partial derivative of Wm dash with respect to theta. So, then this will be MAR to be taken constant outside. So, let me just rearrange this a bit. The MAR, the mutual inductance term in this the mutual inductance term in these three terms here, the MAR is taken out constant. Then IAIR partial derivative of cos theta is minus of sin theta, then minus of sin of theta minus 2 pi by 3 will come out of this particular term, and minus of sin of theta plus 120 degrees will come out of this particular term. Now, if I excite I A, okay. So, now if I excite I A by cos of omega s of t, I B by cos of omega s of t minus 2 pi by 3 and I C by cos of omega s of t plus 2 pi by 3, and I keep theta equal to and I keep theta is equal to omega s plus 2 pi by 3, then this torque expression will simplify to. So, actually I can bring this IR term also outside, right. So, let me do that. Oops, I am sorry. So, it is a bit difficult to bring it out. So, imagine that IR term is taken outside. So, what is going to happen is this M and I am writing now this constant current as capital IR, and then the first term is going to be I m cos of omega s of t times this minus is also taken outside common. So, the minus is also taken out common, and then this is going to be sine of theta. So, therefore, I will write this as sine of omega s of t plus gamma, and then the other terms are I m cos of omega s of t minus 2 pi by 3 sine of omega s of t plus gamma minus of 2 pi by 3 plus I m of sine cos of omega s of t plus 2 pi by 3, that is the current, and the sin theta term is sin theta plus of 2 pi by 3 term will come out to be plus 2 pi by 3. So, the last term corresponded to this I C, and this is what is substituted. So, now if you simplify this, so let me copy it here. Let me copy it here, and now if I simplify it, so first thing is minus of m I r will come out common. Then I am going to use 2 sin A sin B, 2 sin A cos B to be equal to sin of A plus B plus sin of A minus B. So, therefore, to do that I divide this by half and multiply it by half. Then the first term 2 sin A cos B will give me sin of A plus B, which is sin of omega s of t plus 2 omega s t plus gamma plus sin of A minus B, which is sin of gamma, because this minus omega s of t. So, sin of gamma. Then the next one 2 sin A sin B, I am sorry, the next one 2 sin A sin B, what will that give me? That will give me sin of A plus B will be 2 omega s of t plus gamma minus 4 pi by 3, and sin of A minus B, this is A minus of B, will just give me another sin of gamma, and then similarly the third term will be 2 omega s plus t plus gamma plus 4 pi by 3 plus of sin of gamma. Now, you know that these 3 terms add to 0, sin of omega s of t 2 omega s t plus gamma. So, call this some sin of psi. Then the next term is sin of psi minus 4 pi by 3, and the third term is sin of psi plus 4 pi by 3. So, they sum to they being 3 phasors 120 degree apart sinusoidal, they sum to 0, and so this term will become sine of gamma. So, I will get this as minus 3 by 2 m I m I r sine of gamma. So, I will get this as a torque I will get this this torque I will get as minus 3 by 2 I m I r m sine of gamma, and therefore, multiply this by omega of s and I will get the power, and this being peak current, rotor current is DC. So, I will just keep it as IR, but this being peak AC current, if I want to write it in terms of RMS current, then I should write this as IM should be written as root 2 times let us say A phase phasor current. So, then the root 2 and this root 2 cancelling out that factor, I will get minus 3 by root 2 omega s I m I r m sine of omega. This comes out as my this comes as this is m a r, this is m a r, this is also m a r. So, this comes as my torque equation, and for a given omega gamma, therefore, the instantaneous power is now constant and equal to the average power. So, this is we have extended, we have shown what we shown with the 2 phase synchronous motor. Now, we have shown that exactly same thing with the 3 phase synchronous motor, that by having 3 sinusoidally distributed windings in space carrying 3 sinusoidally distributed corresponding currents in time and rotor rotating at a synchronous speed, I can have a constant electromechanical torque to drive my motor, and therefore, a power transfer instantaneous power which is transferred from electrical to mechanical form also will become constant, because the synchronous motor rotates at a synchronous speed. So, we will stop here now. Thank you.